Our next speaker is Aurélien Delphin, who's going to talk about, let me just make sure I get it right, open source tools for within exam automatic brain segmentation for accurate and reproducible geometry planning. And Aurélien did his PhD on MR fingerprinting for microvascular characterization, working both on the simulation and acquisition sides, on preclinical and clinical systems. And he's now a research engineer at Grenoble Alpes University, where he's involved in a lot of projects on many aspects of MR imaging. And that is when he's not away in the Alps for some hiking or skiing, from what I've been told. Without further ado, Aurélien, the floor is yours.
Thank you for the introduction. So, as Sophie said, my name is Aurélien. I'm a research engineer from Grenoble here in the Alps in France, and it has been snowing around, so maybe MRI is not exactly my main concern these days. But I'm glad to be here nonetheless, and I thank the organizing committee for the invitation. So I'm going to present the work that we conducted with my team in respect to a study that was proposed to our MRI facility by a doctor at the hospital. And I'll show you the difficulties we had and how we tried to solve them in the context of a longitudinal study, which meant that we had to plan ahead for different devices, different vendors, and so on. So to illustrate the kind of difficulties we have, maybe let's be honest a second. You have a patient in the scanner, so you must be quick, and you have to place, in this example, a spectroscopy voxel, so a voxel of 3 by 3 by 3 centimeters, and you have to place it anywhere in the brain. So you just have to find the brain of your subject. I think every one of us is able to do that. Maybe now we have to place the voxel somewhere in the left hemisphere. And now here, looking at what I'm showing you here, there's no convention shown there, so maybe the left hemisphere is not that easy to find. Then you have to find the hippocampus. So the hippocampus was that structure here in blue. So I think I could have done that. Now you have to find the middle frontal gyrus, and especially the mid-anterior right section. So this one, I will not have been able to find. It was there in blue. And for a more real-life case, now you have to find a combination of those regions there. And I could not do that. And even the MR techs in our facility had difficulties doing that precisely because the doctor wants a good coverage of the different regions with a single voxel. And we have to be reproducible because it is longitudinal, so the patients are coming several times. That started to be very difficult and to be a concern for our techs. But it's actually what was asked from us by Professor Dondet. And this is in the context of GABA spectroscopy. So you have quite a big chemical shift. The region is quite close to the skull, so it's hard to avoid contaminations. And so both the accuracy of the geometry planning and the reproducibility were an issue. So we thought of solutions for that. So the first thing that we thought of is the automatic volume prescriptions that some vendors propose. So Philips has the Smart Exam, Siemens has the AutoLine, GE has the AirX, and I think all the vendors have something. But first, it's usually limited to a small set of predefined orientations. So the APCP line, for example, which is whole brain imaging. It's not just spectroscopy. And if you want to train those tools for other orientations, you can, but you need quite a number of subjects. And in a research context, and especially on our facility, typically we're going to do 15, 20, maybe 30 patients. That's barely enough to train the the software to find the region that you want. And once the software is trained, your cohort is done. And so there was no, it was kind of useless doing that. So those tools are great for what they do, but they are not really suitable in the research context. And so our idea was to use the open source or at least the easily available tools from the community, such as AssemblyNet that are present here, to perform some segmentation during the exam, during the geometry planning, and to be able to use those directly on the console. So you scan, you use a tool, and you got both results on the console that will help you with your geometry placement. And so that's what we did. Here is what I presented at the ESMR MB in Barcelona. So we actually did that in two different tools. For session one, we focused on the accuracy of the geometry planning. So we perform an anatomical scan, and here on our Philips research, we use Pride research to send those data to an external workstation, where the data is converted to Nifty and then segmented with AssemblyNet. So we obtain that all those masks here, and we are going to select the masks of the regions that interest our study, and we're going to apply those masks on the original anatomical scan and through Pride send it back inside the console. So that's actually what we get back on the console. The regions are segmented, and here on the top right, you can see a spectroscopy voxel that is drawn, and that's how we are going to find a good compromise of coverage between the different regions of interest with our single voxel. So that's one tool that we've made available on our GitHub. And for the second session, we developed a second tool that focuses on the reproducibility of the placements. So again, we acquire an anatomical scan and we send it directly to just export it to our workstation. And in the workstation, there is still the anatomical scan from the first session. So we register those, and that allows us to obtain the matrices that can convert from the space, the patient space of session one to the patient space of session two. And we still have the spectroscopy acquisition from session one, which contains all the geometrical informations that were used on that day. And so we can just convert those geometrical informations, which are in the patient space of session one, to the space of session two using the matrices that we just computed. We obtain a set on Philips. It's just 6 numbers, so you've got the translations on the free axis and 3 rotations, and that allows us, we just input those by hand in the console, and that allows us to ensure that our voxel in session 2 is placed in the same location, on the same location with respect to patient space in session 2. And that allows for a rather good reproducibility. And again, that's a tool that we made available on our GitHub. So doing such thing is already possible on several systems. So here we use the Pride research tool from Philips. We are currently working because the study is multicentric and the other centers have Siemens. We are working with a clinical scientist on implementing that in FIRE, which is the Siemens implementation of the Gadgetron. And I'm sure other vendors could be interested as well. And here, I just wanted to make a small digression here. I think there are two main possibilities to make a tool available. So here we choose the open source approach, which requires to be kind of external. It's very flexible because then it's open and we can do whatever we want, but you need to have a separate machine to do that, which you have to maintain, which you have to integrate in the hospital network, which is maybe the main issue for us sometime. So hopefully people will use that. But maybe in order to make the tool even more usable, it will be good to have it open source so that people know it works, but to have to have an easy integration directly in system. So that will require maybe some help from the vendors. There are, of course, a lot of norms that they must respect. But without being entirely open source. That's to discuss with the vendors. I think something that's directly in system is always easier to use. So there's a compromise to find there, I think. And we tried to make those tools as usable as possible because we knew from the beginning that we had to implement them on other centers. So we made them as low dependency as possible. We used only libraries that supports multi-OS, and we tried to write some good documentation from the beginning. And that's all for me. I think the organizing committee, and I thank you for the attention.